Hello all. Today we discuss the examples of the characteristic method for solving the first order quasi-linear PDE. The problem is we are doing the problem example 2.3 of the textbook Introduction to Partial Differential Equations by Yehuda Pinchover and Jacob Rubinstein. The problem is solve the equation ux equal to 1 subject to the initial condition u of 0 y equal to g of y. So this is the given initial condition. So first of all, from the given equation, given PDE, first we write the characteristic equations. So the characteristic equations of the PDE are given by ux equal to 1. So a equal to 1, therefore dx by dt in terms of t comma s equal to a, that is 1 dy by dt of t comma s. Since there is no uy term, this will be 0, and du by dt of t comma s is equal to 1. So these are the characteristic equations. Let this be number 1. Sorry, this will be number 1, this will be number 2. Okay, now the initial condition is given as u of 0 y equal to g of y. The associated initial condition u of 0 comma y equal to g of y. Therefore, the parametric form is so the parametric form is x. We have the equation is u of 0 y equal to g of y. So the parametric form will be here x of 0, x naught of 0 is equal to 0. So y coordinate we are taking as the variable s. So y naught of s equal to s. So in terms of y naught, we have u is equal to g of y. So u naught of s is equal to g of s. Put it as equation number 3. Now integrating the characteristic equations or system of characteristic equations with respect to t, we have x of t comma s equal to t plus some function of s, let it be f1 of s, y of t comma s equal to integrating 0, it is 0 plus f2 of s, then u of t comma s is equal to du by dt is again equal to 1. So it will be t plus f3 of s. Now at t equal to 0, from these equations we have x naught of s, x of 0 comma s, which is denoted as x naught of s, will be f1 of s, y naught of s will be f2 of s, and u naught of s is f3 of s. Now comparing this with equation number 3. Comparing 5 with equation 3, we have both are giving the initial values. So x naught of s is f1 of s. From equation 3, x naught of s equal to 0. We can eliminate the functions, or we can find the functions in terms of S, f1 of S as 0, f2 of S is S, f3 of S is u0 of S. From equation 3 it is g of S. So this is our functions f1, f2 and f3 respectively. Therefore, substituting this in equation 4, we have the parameterization of the curve integral surface. X of t comma s is t, y of t comma s is f2 of s. Actually x is 0, isn't it? Yeah, y of t comma s is f2 of s, that is s. Now u of t comma s will be t plus f3 of s, t plus g of s. So this is the parametric representation or parameterization of the integral surface. Integral surface u. Okay. Now from this equation or from this parametrics form, we can write t and s in terms of x and y very easily. So in the xy transformation, we have the integral surface u of x comma y is equal to x comma y. X is, instead of t we can write x, instead of s we can write y. So u of x comma y will be x plus g of y. So this one will be the corresponding integral surface. Now we may consider some notes. First one, suppose we are taking the initial condition instead of u of 0 y. If the initial condition is u of x comma 0 equal to some function of x, then we will see what happened to the integral surface. Okay, so the parameterization will be the parametric form or the parameterization is, we have x naught of s, we are taking the variable as s, then y naught of s given as 0 and u naught of s is h of s. Okay, now as we know what is up to equation 4 it is true. No, there will be small change in the characteristic equation. No, there is no change in the characteristic equation since they are obtained from the initial value, I mean the PDE, not depends on the initial condition. So that the characteristic curves are given by 4. So from equation 4, let this be equation number 5 is there, let this be 6, this be 7. Okay, so from 5, which gives the characteristics at the point t equal to 0, from 5 and 7 we have f1 of s will be s itself. F1 of s is at t equal to 0, x naught is f1, y naught is f2, u naught is f3. So comparing this with equation number, f1 of s is s, f2 of s is 0 and f3 of s is what? H of s. Therefore, the parameterization of the integral surface is, what will be the parameterization? X of t comma s. What is x of t comma s? It is t plus f1 of s, that is t plus s, and y of t comma s. What is y of t comma s? It will be f2 of s, and we know f2 of s is 0 itself. Now u of t comma s. U of t comma s is t plus f3 of s. F3 of s is h of s. Okay. So this is the parameterization of the integral surface. Now we have to convert this into xy transformation into t of x of t comma s and y of t comma s to t of xy s of xy. അതായത് ടീനെയും എസിനെയും മാറ്റിയിട്ട് എന്ത് വരണം, എക്സും വൈയും വരുന്ന ഒരു ട്രാൻസ്ഫോർമേഷൻ അല്ലെങ്കിൽ എക്സ് വൈ സിസ്റ്റത്തിലേക്ക് നമുക്കിത് മാറ്റണം. But since y is equal to 0 here, we know there is no possibility for converting this directly, or such a conversion of this is not possible. The transformation of x of t comma s comma y of t comma s the transformation, we have to invert this. Transformation cannot be inverted here. So there is no solution at all. The possibility is there will be no solution. What will be the condition? What will be the reason for this? From the transversality condition, we can see the Jacobian of these two. Jacobian in this case, Jacobian is a determinant AB dx naught by ds dy naught by ds. What is a here? A is 1, b is 0. Then dx naught by ds. What is dx naught by ds? D by ds of, what is x naught in this case? X naught is s. So dx naught by ds is 1. dy naught by ds is d by ds of 0, that is 0. This is obtained from equation 7. Okay, so again this is 1 0 1 0. So the determinant is 0. So the Jacobian is 0 here. So the problem will have will in general no solution at all. If it is possible to find one solution, then there may be infinitely many solutions in this case. But in the when we taken the initial condition as u of 0 y equal to g of y, we have obtained a unique solution. This may be because if we consider the Jacobian here, this will be dx naught by ds is 0 and dy naught by ds is 1. So 1 0 0 1, whose determinant is equal to 1, which is not equal to 0. That means the Jacobian is inverted. So there will be a unique solution in this case. But when we change the initial condition as u of x0 as h of x, then it is not possible to find the solution. Geometrically, this is because the projection of the initial curve is here. The projection of the initial curve, in this case the projection of the initial curve is y naught of s equal to 0, x naught of s equal to s, u naught of s equal to h of s. Projection to the xy plane is obtained by taking u equal to 0. So here this will represents x naught of s equal to s and y naught is equal to 0, y equal to 0, that is x axis. So geometrically here the projection of the initial curve is precisely the x-axis, which is exactly the or which is also the projection of a characteristic curve. Projection of a characteristic curve. So since both are same, that is why there is no solution at all. Actually, we need to find the characteristic curves that originates from the initial condition or initial curve. So this will not happen here, since both one will coincide or both are same. Projections of the characteristic curve is same as projection of the initial curve here. So there is no solution at all. Now we may discuss the definition of characteristics. Okay, characteristics. So characteristics means the projection of the characteristic curve on the xy plane is termed as characteristics. The projection of the characteristic curves. The projection of the characteristic curves on the xy plane. This is termed as characteristics. So this one will be the characteristics which may determine the solutions or the possibility of or uniqueness or the possibility of the solutions. And we may note that the projection of a characteristic curve is given by the condition. The projection of a characteristic curve is given by the condition S equal to a constant. So in order to find the characteristics of the given PDE, there are several methods available. One of them is to solve all the characteristic equations or characteristic curves, and then to project the solution on the xy plane. This is one method. And the substituting the condition that is s equal to into the equation that is equal to s of xy determines an explicit equation for the characteristic. Okay, now an alternate method is obtained or is valid whenever the PDE is linear. So whenever the given PDE is linear, that means it will be of the form a of xy ux plus b of xy uy equal to some function a of xy or c of xy into u, right? So that means these functions are explicitly independent of the variable t, so that our characteristic equation dx by dt equal to a of xy, dy by dt equal to some b of xy, which are independent of the variable t or independent of the equation du by dt. So from the first two equations we can write what will be dy by dx. So dy by dx means dy by dt by dx by dt. So dy by dt is b and dx by dt is a. So b, which are both are independent of the variable t. So we will get an equation like this, and solving this we will get the first order or we will get the characteristics. Okay, required characteristics. So in these two methods, in any of these two methods, we can adopt the required or possible one and find the uh, characteristics. For example, find the characteristics to solve or for the linear equations of the form what is the form a of xy ux plus b of xy uy equal to 0. So this is the given equation whose right side is equal to 0 and a and b are functions of x and y which are independent of the variable t. Therefore, the equations for the characteristic curves or the characteristic equations are dx by dt equal to a, dy by dt equal to b and du by dt equal to 0. So a, b both are independent of x and t, the variable t. Therefore, the solution is this one implies that the solution du by dt equal to 0, which implies that the solution is u is a constant on the characteristics. So u is a constant on the characteristics determined by characteristics are dy by dx equal to b of xy by a of x comma y, b by a. Now for example, in this problem, if a equal to 1 and b equal to root of minus x, what will be the solution? So the characteristics will be dy by dx equal to b by a minus root of minus x by 1. So root of minus x. Now we need to solve this equation which gives the characteristics. So by variable separable we have dy equal to minus x raised to 1 by 2 dx. Okay, integrating on both sides we have y is equal to, here it will be minus x raised to 1 by 2 plus 1, that is 3 by 2 into 2 by 3 into minus 1 into minus 2 by 3 plus some constant. Now multiplying this equation by 3 by 2 and adding the x term to the right. So we have 3 by 2 y plus minus x raised to 3 by 2 equal to 3 by 2 c1, let it be c. Therefore the characteristics are given by 3 by 2 y plus minus x raised to 3 by 2 equal to a constant and u equal to a constant on these lines. These are the characteristics in the given problem. Okay. Okay, so this about the method of characteristics, and we have done one problem related to that method, and we can see that the changes in the initial conditions may depend or may affect the existence and uniqueness of the solutions or existence of the integral surface for the given problem. Okay, so let's stop here. Thank you.